All right, next up, we're going to talk about the common ion effect, which is essentially just an application of Le Chatelier's principle. So let's take a look at it here as a theoretical example. Say silver iodide, right, dissociates into silver and iodide, right? So say you had a solution that you know had some silver in it, right? So, and you want to get the silver out because silver is valuable. So say you want to precipitate silver iodide because silver is valuable, and you've got some solution with silver in it, so you want to get it out so you can, sell it and make some money, right? So what could you add to make it precipitate out? And so, yeah, you could add more silver to it, but then you're kind of right back where you started, right? You actually just kind of got a worse effect, right? You lost some silver. So instead, what you could do is you could just add a whole bunch of I minus, right? As we increase the concentration of I minus, we will shift the equilibrium to the left and precipitate out silver iodide, right? So this is just an application of Le Chatelier's principle. And so, for example, maybe you could add some potassium iodide, some sodium iodide, whatever, something with iodide. Iodide is very cheap, and so you could use it to get this thing out as well. And so, as we've previously seen, other things can be common ions, such as H plus and hydroxide. So acids and bases can be common ions. And we have to keep an eye out for coupled reactions, right? Things that might not necessarily directly affect the things, but might, sideways affect one of the concentrations. So in this case, magnesium hydroxide dissolving into magnesium 2 plus and 2 hydroxides. If we have a high pH and then a low pH, go ahead and tell me which way is that going to shift the equation. So if we have a high pH, that means that we added base to it. Remember, high pH is more basic solution, and so we've increased the concentration of hydroxide. If we increase the concentration of the hydroxide, that is a product, and so we will shift to the left, right, if we increase it. And then vice versa, if we have a low pH, that means that we added some acid or some H plus. Now you don't see acid directly involved in this equation, right? There's no H plus, but you got to think about some coupled reactions. In this case, H plus and hydroxide will react to make water. And so if hydroxide is reacting to make water, its concentration will actually decrease. Let's see what color, make this green. So its concentration would actually decrease. So you're decreasing the amount of product and you're going to shift yours towards the right. So if you want magnesium hydroxide to dissolve, you should add some acid. We can also think of some other examples. So what would happen if we added some magnesium chloride to this solution, some potassium hydroxide, some sodium nitrate, or some HCl. So looking at all of these examples, magnesium chloride, has this magnesium in it, right? So you're going to increase the amount of product, right? And so we're going to shift to the left, right? This potassium hydroxide has more hydroxide in it, so you're going to increase the amount of product, and so you're going to shift to this left. This sodium nitrate, we don't see sodium anywhere. We don't see nitrate anywhere. We know that both sodium and nitrate are neither acidic nor basic, so they won't affect the pH, and so this one will have no effect. And then finally, if we add some HCl, the HCl is going to react with the hydroxide, lower the concentration of the hydroxide, and thus shift the reaction towards the right, right? Same thing when we increased acid because it's basically the same thing.